Good morning. Greetings from Beatrix Technologies. I am Sangeeta, your instructor for the course on Maths for Machine Learning. The objective of this course was to refresh the basics in mathematics for higher level courses in machine learning and data science, and to build an intuitive understanding of the mathematical concepts relating them to machine learning and data science. As a part of it, we have finished the first module on linear algebra, where we had discussed the concepts of vectors and matrices, the concept of eigenvalues and eigenvectors, and how these are used in singular value decomposition and principal component analysis. Today we would be discussing the topic of multivariable calculus, where we'll start with functions of single variables and move on to look at functions of several variables. We'll discuss the concept of derivatives and gradients and the concept of maxima and minima. The concept of maxima and minima helps us in optimization of the error function. We'll also discuss the gradient descent algorithm and its variant, the stochastic gradient descent algorithm. So the content for today is, we'll start with the concept of what is a derivative. How do we differentiate a single valued function? We'll extend this to the differentiation of functions with more than one variable. That is what we discuss in multivariate calculus. We'll discuss the concept of partial derivatives, gradient descent, and finally we will see how gradient descent is used in machine learning algorithms. Let's begin with understanding what is meant by a function of a single variable. So a function y is equal to fx is a rule for determining y when we are given a value of x. From our school days, we have been seeing these graphs where we plot x on the x-axis and we draw a line. Now this line represents the line y is equal to 3x plus c. So this is an example of a function in a single variable x. Now how does this line help us? Looking at the graph, we can understand that when x is 0, y is 6. When x is minus 2, y is 0. So likewise, the line helps us to find the value of y given any value of x. For example, if I want to find out what is fx when x is equal to 2, then I substitute the value of x here. We get 3 into 2, 6 plus 6, y is 12. Similarly, let's consider example of another function. Here fx is equal to x square. This is the graph, a parabola, which represents fx is equal to x square. Here too, we see that when x is 0, y is 0. And for any other value of x, we can just put the value of x in the function and get a corresponding value of y. So when x is 2, y is 2 square, which is 4. Now let's move on to what is meant by a derivative. The meaning of a derivative is understood from two perspectives. The first way is a geometric perspective, where the derivative is the slope of a curve at a point. That is the angle which the tangent at the point makes with the x-axis. I think you all can recall this concept of geometrical thing when you had read about tangents in your school. Essentially, the tangent represents how much a curve is changing at a particular point. The second perspective is the physical perspective, where we talk about derivative as the rate of change of y. So we'll see both of these perspectives, and we see that both of them are related to change. So let's recall first what is meant by a tangent line. A tangent is a line that touches the curve at only one point. So here, if you look at it, this red line is a tangent line. This is a tangent line. But this is a line which passes through the curve, so it is not a tangent. Likewise here, this line is a tangent line, and this line which meets the circle in 2 points is not a tangent line. Now what is a second line? Let us look at the red line here. We see that this line cuts the curve at 2 points, so it's not a tangent. Now let us try to evaluate the slope of this line. So if you look at this figure, at x equal to a, this height I have marked it as f of a, the point on the curve. When we change x by a small value h, say x goes to xa plus h, then the point on the curve moves from f of a to f of a plus h. Now, we all know that the slope of the line is y2 minus y1 over x2 minus x1. Now observe here, what is y2? y2 is f of a plus h and y1 is f of a. So y2 minus y1 becomes f of a plus h minus f of a, and x2 is a plus h, x1 is a. So the denominator is a plus h minus a, and this simplifies to f of a plus h minus f of a by h. Now what happens when this h becomes smaller and smaller? So this line keeps the 2 points of intersection keep coming closer and closer, and we observe that as h becomes smaller, the second line tends to the tangent line. So what we can write? We can write limit h tending to 0 of f of a plus h minus f of a by h. And now this is nothing but the slope of the second line now becomes the slope of the tangent line at x equal to a. So let us just take an example. Suppose we want to determine the slope of the tangent line at x equal to 0 for a given function fx equal to 6x square minus 4x. So this is the graph of 6x square minus 4x, and we are interested in this tangent. We want the slope of this tangent. So slope means the angle which this tangent makes with the x-axis. So we will evaluate like as we did in the previous slide. Here a is 0 because we are finding the tangent at x equal to a. So we have limit h tending to 0, f of 0 plus h minus f of 0 divided by h. Now we'll substitute the value of f of h here. How do we do it? Replace x with h. So we will have 6h square minus 4h divided by h. And f of 0 is 0 itself. So we don't get the second term. We only have f of h. And now before we put this limit h tending to 0, we can cancel the common h from the numerator and denominator so that we get 6h minus 4. And the limit h tending to 0 gives us a minus 4. Now let us look at the second perspective of derivatives, where we look at derivative as a rate of change of y with respect to x. So consider a function y is f of x. Now let's increase x by a small amount, delta x. So x becomes x plus delta x. So inside fx we replace the x with x plus delta x. Now when x changes from x to x plus delta x, you can see in the figure that y would also change from f of x to f of x plus delta x. Let us denote it as y plus delta y. So we look at the expression y plus delta y is equal to f of x plus delta x. Now we subtract y is equal to fx from this expression. So we will get y plus delta y minus y is f of x plus delta x minus fx. When we simplify this, we will get delta y is equal to f of x plus delta x minus fx. Now when we talk of a rate of change, we want to see how fast y changes when x changes by a quantity delta x. So to get this rate of change, we divide delta y by delta x, and when we divide by delta x on both sides, we get f of x plus delta x minus fx by delta x on the right hand side. Now if you look at it, this expression looks very similar to the expression on the previous slide, where we had a f of a plus h. So now we are replacing delta x by a. There a small change in x was h, a plus h. So x was a and we shifted it to x is a plus h. So the delta x is equivalent to h, and the point x, the value where we start is a. So f of x plus delta x corresponds to f of a plus h, and f of x corresponds to f of a, and replace delta x by h. So we can see the similarity between the expressions of dy by dx and the slope of the tangent at a point x equal to a. Now here, if we make delta x tend to 0, that means we are trying to bring this point x plus delta x closer and closer to x, because we are trying to map it to the concept of tangent. Just as we took a limiting case of a tangent from the second line, we will make this delta x smaller and smaller. So when we make delta x tend to 0, we call it dx. So dx is an infinitesimal increase in x. Likewise, delta y becomes a very small increase in y and we call it dy. So delta y by delta x, we replace it by dy by dx. And now when we take the limiting case, limit delta x tending to 0, delta y by delta x, we call it as dy by dx. So we get the definition of derivative as dy by dx is f of x plus dx minus f of x divided by dx. So this derivative is the rate of change of the function fx with respect to x. Note that the derivative will also be a function of x. Also, the existence of the derivative will depend on whether this limit delta x tending to 0 exists or not. Although we will not spend our time on understanding the existence of a limit, but we can understand this with the help of a picture. We'll do it shortly. So let us first understand the comparison between these two perspectives of derivatives which we have talked about. So we saw that delta y by delta x is f of x plus delta x minus fx by delta x. So we also saw that the slope of the second in the limiting case when delta x tending to 0 becomes the slope of the tangent. So this expression delta y by delta x is actually the average rate of change or an average velocity. But the moment we make delta x tending to 0, when we move from a secant to a tangent, the definition of derivative becomes limit h tending to 0, f of a plus h minus f of a by h. Now this is the slope of the tangent at the point x equal to a. So when we take dy by dx at x equal to a, it is the value of the derivative at a particular instance a. So the slope of the tangent is nothing but the rate of change at an instance x equal to a. So this is called as the instantaneous rate of change or the instantaneous velocity. So now note this, that when we find dy by dx, it ends up as some function of x. It is not restricted to an instance. It is just the rate how y will change with respect to x. But when we talk about the slope of the tangent, it is the value of dy by dx at a particular point x equal to a. So it means that we can use the concept of derivative, we can evaluate dy by dx and use it to find the slope of a curve at a point. Now, the definition had a term if the limit exists. So what does it mean? So let us look at a function fx is equal to x minus 3. So what at x equal to 3, the function is 0. So f of x is 0 here. For positive values of x, when x changes from 3 to 4 or 3 to 5, this is the line. For negative values of x, when x goes to minus 3, since it's an absolute value function, this is still a positive value, but x takes negative values here. So f of x minus delta x is this line. You can plot this and get a feel of it. Now what happens here? We get a corner point. So when the curve has such corner points or sharp points on the graph, the derivative does not exist here. This is because if you look at the slope of the tangent from this is the slope of a line, it is positive here. The angle which it makes with the x-axis is positive here. If we take the slope of the tangent from the left, it is a different value. It's a negative value. So when we do not get the same value of the slope from the left hand side and the right hand side, we say that the derivative does not exist. This intuitive feeling is enough for now. We need not go in detail into the concept of limits. Now let's move on. We have understood what is meant by a derivative, which is nothing but the rate of change of a function with respect to its independent variable. That is the rate of change of y with respect to x. So let's see how do we evaluate these derivatives. So let's take the simplest case when y is a constant. So this is the line y is equal to constant. And now as I am saying y is a constant, what does it mean? For every value of x here, y is c. So y is not changing with c. So in this case, what should happen? The rate of change of y with respect to x should be 0 because it is not changing. And you can also check from the concept of slope now here. This is a line parallel to x-axis and therefore it has a slope 0. So d by dx of a constant is 0. Now let's look at a line. The line y is equal to x. Now see here, for x equal to 0, it is 0. When x is 1, you can evaluate from the function. So y is 1. When x is 2, y is 2. Now in this case, suppose I have to evaluate the rate of change. What we will get? We will get, suppose at x is 1, y is 1. This is the line. And at x is 2, y is 2. So when we take the difference, we will get the numerator y2 minus y1 as 2 minus 1. And the denominator will also be x2 minus x1 is also 2 minus 1. So the slope is dy by dx will be 1. Now likewise, if we take the line y is equal to minus x, here when x changes from minus 1 to minus 2, the change is minus 1. The change is minus 1, but y changes from, y will also change from minus 1 to minus 2. Yeah, so observe here, when we are changing x from minus 1 to minus 2, delta x is minus 1. We are adding a minus 1, but y changes from 1 to 2. So what will happen? The change in y is positive here, but the change in x is negative. So dy by dx will be minus 1. We also say that this is an increasing function. Y increases as x increases. In this case, we say that y decreases as x increases, because you have to understand that the increase of x is this side. From minus 2 to minus 1 is increasing value of x when we talk of the negative side of the x-axis. So y decreases as x increases, and this is represented by a negative slope. Dy by dx is minus 1, whereas an increasing function is represented by a positive value of dy by dx. So let us recap. The rate of change of a function is measured by its derivative. When the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. Now let's move on and see the derivatives of some power functions, higher powers of x. Now all these can be evaluated by the fundamental definition limit h tending to 0, f of a plus h minus f of a by h. But we need not get into that. We have all predefined formulas to find out the derivative of functions. So we start with the power function, the most basic one. So we want d by dx of x to the power n, and this is given as n x to the power n minus 1. For example, when n is 3, fx is x cube. Then if we use the formula, we have to substitute n equal to 3 here. So we will get 3 into x to the power 3 minus 1, that is 2. So f prime of x will be 3x square. Likewise, if we consider another function, 2x to the power 5, then 2 will remain as it is. We are only differentiating x to the power 5. So the scalar we can bring it out, and now we will have n is equal to 5 and into x to the power 5 minus 1. So we get 10x4. Let us look at one more function. Fx is square root of x. Now here, in order to use this formula x to the power n, we will express the square root as x to the power half. And then now we will substitute n is equal to half. So we will get half into x to the power half minus 1. So this would become half x to the power minus half. Or you can write it as 1 by 2 root x. Let's take one more example. This is 9 by cube root of x. So 9 is a constant. We will keep it as it is. We have to only differentiate cube root of x. Now this cube root of x is in the denominator. So first we can write it as x to the power 1 by 3. And when we take it to the numerator, this will become x to the power minus 1 by 3. Now if we compare with x to the power n, n is minus 1 by 3 in this case. So we will find f prime x as 9 is retained as it is, minus 1 by 3 into x to the power. Observe, we are putting n is minus 1 by 3, minus 1 by 3, minus 1. So if you simplify this, this will be minus 3 minus 1 by 3, which is minus 4 by 3. So we get minus 3 into x to the power minus 4 by 3. So this is how we can evaluate the derivative of any power of x. Yeah, so this is an exercise for you to once again recap your concept of slope. Fx is x squared, so this is a quadratic function. And understand that the derivative of a constant will be 0. So derivative of f of x is 2x, and you will evaluate this derivative at every point. So at x equal to minus 3, it will be minus 6. So that is the slope of the tangent at x equal to minus 3. Likewise, if you put 2x, x equal to minus 2, so we will get minus 4, which is the slope of the tangent at x equal to minus 2. So this I leave as an exercise to you to finish this table. Now let us move to the next concept, the sum and difference rule. Now what does the sum rule say? If you have two differentiable functions, so fx and gx, just as in the previous slide, we can say we had two functions, x squared plus 1, which 1 was a constant. So when we have to differentiate these two functions, which are sum of, we have to rather differentiate the sum of two functions, fx plus gx, then the derivative is we take the differentiation of the individual functions and add it. So we will have d by dx of fx plus d by dx of gx. Similarly, the same concept can be extended to the difference rule. The differentiation of fx minus gx will be d by dx of fx minus d by dx of g of x. So here is an example. Here we have taken fx is equal to 2x cube plus 3x square minus 12x minus 5. Now this function fx is the sum of four functions. One is 2x cube, 3x square, 12x and 5. So what does the sum rule say? That we can differentiate each of these functions individually. So we will go back and use our power rule. So 2 remains as it is. And we have seen that differentiation of x cube, when I put n equal to 3, this is 3x square. So we will do this. So for x cube, we will write 3x square. So 2 into 3 will give me a 6x square. Now differentiate 3x square. For x square, it is 2x to the power 2 minus 1. So it is 2x, and 3 into 2x gives us 6x. Differentiation for y equal to x, this is just x, so it is 1. We get a minus 12, and we have seen differentiation of a constant is 0. So for d by dx of 5 gives us 0. So what we have done? We have done the differentiation of each of these individual terms and just added the derivatives. So this is what sum rule tells us. So here is another example where you are using the sum and difference rule. Now the difference rule is nothing but the same as sum rule. Wherever you have a minus sign, you leave it as a minus sign. And now here you have to do, I will just explain the first step, and then you can use your formula for x to the power n and verify the last two steps. So this will split up as d by dx of x to the power 8 plus 12 times. This constant you can always bring out as a scalar. D by dx of x to the power 5 minus 4 d by dx of x to the power 4 plus 10 d by dx of x cube minus 6 d by dx of x and finally d by dx of 5. So now each of these derivatives of x8, x5 you will evaluate using the derivative of a power function and then you will simplify. So this you can complete it and see. Now let's move on to the product rule. So if you have two functions fx and gx and we want to find the derivative of their product, that is we are interested in d by dx of fx into gx. So here I consider fx as the first function, say gx is the second function. So we first write fx as it is and multiply it by the derivative of g of x. Then we add to it, we keep gx as it is and we find the derivative of fx. So we can read it as first function into derivative of second plus second function into derivative of first. So let's take an example where fx is x square into 3x plus 2 and we take gs is x square. And we also take one hx is 3x plus 2. So we will find, we are looking at fx as the product of two functions. So here, understand it like that. We have fx is x square into 3x plus 2. So one component of it, so it's a product of two functions. The first component, as I said, the first function, I'm representing it at gx, so that is x square. And the second part, I'm representing it at hx, which is 3x plus 2. So the derivative of fx is nothing but the derivative of gx into hx. So we differentiate each one of them and first find out what is g prime x. So we know that g prime x is 2x and here we can see that h prime x is 3. Now we use the product rule. So what does the product rule say? F prime x is derivative of first, that is g prime x into hx and plus gx into h prime x. Since it is addition, it's commutative, it doesn't matter which you write first. So we can take 2x into 3x plus 2 plus x square, that is gx, into the derivative of hx, which is 3. And this gets simplified to 6x square plus 4x plus 3x square. Okay, so here we are just expanding the brackets and then we group the like terms. So 6x square plus 3x square becomes 9x square plus 4x. So that is how we find the derivative of a product of two functions. Okay, so we will differentiate each one of them individually first and then we will use this rule. Next is the quotient rule. What if we have a division of two functions? So we have one function in the numerator, which is like x here as shown in the example, and gx is another function in the denominator, which is 3x plus 2 here. And we are interested in finding d by dx of x by 3x plus 2. So what we do here, we call one as the numerator and let me say this is my denominator. We take the square of the denominator here. Then we have, I read it as denominator, the differential of numerator. See, fx is the numerator. So write the denominator as it is, the differential of numerator minus numerator into differential of denominator. So let us try to use this for this example. So observe here, we have gx is x, that is my fx, the numerator, and hx is 3x plus 2. So the function fx is x by 3x plus 2. I am splitting it into two parts. One is the numerator, which is denoted by x, and the denominator hx is 3x plus 2. So first we'll get the derivative of the numerator and denominator separately. So g prime x is 1, h prime x is 3. Now let us apply the quotient rule. So as I said, the quotient rule is So quotient rule here tells, now look at it here, this is denominator. So where is my denominator? Denominator is hx. So we have written hx as it is into differential coefficient of numerator. So that is g prime x. Then we have the numerator, which is gx, so written as it is. And the differential coefficient of denominator is h prime x. So denominator, differential coefficient of numerator minus numerator, differential coefficient of denominator. And here we have in the denominator square. So let us substitute these values. You see g prime x is 1, hx is 3x plus 2, gx is x, and h prime x is 3. So we substitute this value and we just simplify this algebraic expression and we'll get 2 by 3x plus 2 whole square. So this is how we use quotient rule when the function consists of a fraction of two functions. Okay, so we have one function of x in the numerator and we have another function of x in the denominator. In such a scenario, we use the quotient rule. So here is another example, and this I think you should work it out yourself. I will just explain. Here your numerator is x square plus x minus 2. So consider this as gx, and this is your hx, x cube plus 6. That is your denominator. So how we have found dy by dx? As I said, let me repeat, denominator. So we have written x cube plus 6 as it is, and we have taken d by dx of the numerator, that is x square plus x minus 2, minus numerator, which we have written it as it is, and we have taken d by dx of x cube plus 6. Okay, so we are using the same quotient rule. Denominator, differential of numerator minus numerator into differential of denominator. And in the denominator, we have taken this x cube plus 6 whole square. So to understand this expression, as in the previous slide, assume the numerator is g of x and the denominator is h of x. Now we can just simplify. This remains as it is. Now look at it. Here we are using the rule, the sum rule. This function is a sum and difference of three functions. So for x square, the derivative is 2x. For x, the derivative is 1. And 2 being a constant, the derivative is 0. The next one, we get x square plus x minus 2. And derivative of x cube is 3x square. Understand n, x, n minus 1. I am trying to recall here. So we will get n is 3, x to the power 3 minus 1, that is 2. And again the differential of a constant is 0. And now further you can simplify. You can do the expansion of these terms and we can collect the like terms to get the final derivative of dy by dx in this form. So these two steps, just work it out. Simplify the algebra and you will get the expression. Now we move on to the chain rule. Now this rule is applied when we have a function embedded inside another function. We call it as a function of function. What it means? Look at this example. Fx is 5x cube minus 6 to the power 4. In this, if I try to replace 5x cube minus 6 with a variable say u, then I can write y is fx is u to the power 4. So what it means, u is itself a function of x. So let me represent u as g of x. And then f is a function of g of x raised to the power 4. So how we represent it? Y is f of u, u to the power 4. So y becomes f of u. And u is a function of gx, that is 5x cube minus 6. It is a function of x. So we can write y is f of g of x. So this is what we mean by a function embedded inside another function. So gx is itself a function and f is a function of it. So in such cases, how do we differentiate? See, we have considered the differentiation of sum of two functions, the difference of two functions. Then we have talked about fx into gx when we have a product of two functions. And we have also seen when we have a division of two functions, how do we differentiate when it is gx by hx. Now we are talking of a function inside another function. So f of g of x. So how do we do it? So we look upon dy by dx. Now you see y is a function of u. Y is u of 4. So I can always differentiate y with respect to u. So understand, whenever we say y is a function of some variable, that variable is the independent variable and y is the dependent variable. So we differentiate y with respect to whatever is that independent variable. So here I am talking of dy by du. Now next, u is a function of x. So I can always differentiate du by dx. Now I can combine these two. I can write dy by du into du by dx. And you see this du and du, we don't say we cancel it, but they can be considered as a sort of cancellation, and you will get a dy by dx. So when we have a function of function, we take the product of this chain of derivatives. So we first differentiate y with respect to u, and then we differentiate u with respect to x. So that is what is written here. When you have a function of function, differentiate y with respect to u, differentiate u with respect to x, and then multiply the two results to get the derivative of y with respect to x. So let us do it and see. We'll use this chain rule now. Dy by dx is equal to dy by du into du by dx. So we get y is f of x, the same function we are using. We substitute 5x minus 6 is equal to u. So y becomes u of 4. Now I can differentiate y with respect to u. So we get dy by du and apply your power law. 4 is n. So 4 u to the power n minus 1, that is 4 minus 1. We get dy by du is 4u cube. Similarly, if we try to find out du by dx, we will get du by dx. Here we have to differentiate x cube. So 3x square. So we will get 15x square. And derivative of 6 is 0. So now we have both these derivatives, dy by du and du by dx. So we will make use of the chain rule. Dy by dx is dy by du into du by dx. Substitute the values that you have obtained here. So replace dy by du with 4y cube and du by dx as 15x square. And now since we want the derivative as a function of x, u is a function which we have brought in by substitution. U was not there in the initial definition of the function. So your final result has to be in terms of x only. So what we do after this, we replace this u with 5x cube minus 6. So we will get 4 into 5x cube minus 6 cube into 15x square, which can be simplified to get 15 into 4. This should be 60. Sorry, here there is a mistake. Corrected. It's not 45. We'll get a 60x square into 5x cube minus 6 whole cube. So work it out and correct this step. So here there is another example of chain rule which I will expect you to work it out. So here we have fx is x square minus x minus 1 inverse. So once again we'll take fx as made up of two functions. So the inner function will replace it with u. So we call u as x square minus x minus 1. And then now y will become, when you substitute this as u, y will become u inverse. So once again we will find dy by du and du by dx and then multiply them together to use the chain rule. Now here be careful, dy by du is the differentiation of u inverse. So n is minus 1 here. So take n is equal to minus 1, n into u to the power n minus 1. So it will become minus 1 minus 1. So this will be minus u to the power minus 2. Take a moment and think here and simplify this. Now du by dx will be, this is simple, for x square we get a 2x and for x we get a minus 1. So next is the simple step. Just substitute these values, minus u to the power minus 2 into 2x minus 1. And once again we have to replace u back in terms of x because the final result we want only in terms of x. So replace u with this minus x square minus x minus 1 and simplify to get the final result. So from this step again I think you can work it out. Now let's move to the concept of higher order derivatives. So we have been doing the first order derivative all the time. Now when we take the derivative of the derivative, that we call as the second order derivative. So let's consider this function y is equal to 3x cubed minus 2x plus 1. The first derivative is given by dy by dx. This is the usual thing which we have been doing. So dy by dx is 3 into d by dx of x of 6. So that will be 6x5. And 6 into 3 will give me 18. So we will get 18x5. And the derivative of minus 2x will be just minus 2. Derivative of 1 will be 0. Now when we differentiate this dy by dx, once again, this is also a function of x and it can be differentiated further. What we get is a second derivative. So the notation for second derivative is d2y by dx square. So we put a 2 here and a 2 here. Be careful. It is not dy by dx whole square. We read it as d2y by dx square. This is nothing but d by dx of dy by dx once again. So now you differentiate dy by dx. It is the derivative of x to the power 5. It is 5x to the power 4. So 5 into 18 will give me 90 x to the power 4 and the derivative of constant is 0. Now we can extend this to the third derivative if you have understood the second. So it is going to be d by dx of d2y by dx square. So we take the derivative of whatever we have got in the previous step. And the notation for this is d3y by dx cube. So we said d3y by dx cube is nothing but d by dx of d2y by dx square, which is, now you differentiate x4. x4 is 4x cube and 4 into 90 will give 360. So the final result will be 360x cube. So all these things you need to work it out. Take a paper pencil and do it and see. You will get a feel. Every time we are making use of the formula d by dx of xn is nxn minus 1. So keep using that. It will be very easy to get all these results. So let us recap. These are actually some of the very basic differential formulas. You have a lot of formulas which you can always Google. But to get an understanding for machine learning, you just need to understand what is this concept of derivative and some of the basic formulas. If you get a function which is different from these functions, you can always Google and find out what is the derivative of that function. So we have already seen x to the power n is nxn minus 1. When you have a constant CF derivative, C we don't differentiate. We have been seeing that. Like in the previous slide, if it is 90x4, I don't do anything to 90. I just differentiate x to the power 4. So, just a moment. Yeah. So, CF prime becomes C of F prime. So, the constant is taken as it is and we differentiate whatever is the function here. The sum of two functions, f plus g prime, is f prime plus g prime. So, either we say d by dx of fx or we say f prime x. Both are same notations. You will find both being used. So in short, we write it as f prime of x. So when I say f prime, it is df by dx. F minus g prime is f prime minus g prime. Fg prime, this is the product of two functions. So this is the first function f into the derivative of second plus second function g into the derivative of first f prime. Likewise, we have also seen f of g prime. This is g square, the denominator square. Denominator, differential of numerator minus numerator, differential of denominator. So we have gf prime minus fg prime by g square. Now here I have just listed out some of the formulas. Wherever you need, you can use it. Just as you have been using x to the power n, you can just make, wherever you find a log of x, the derivative of log of x, you can write it as 1 by x. Derivative of sin x is cos x. Derivative of cos x is minus sin x. Derivative of tan x is sec square x. D by dx of e to the power x is e to the power x. D by dx of cot x is minus cos x square x. D by dx of sec x is sec x tan x. And d by dx of cosec x is minus cosec x cot x. So in this first unit, we have discussed what is meant by differentiation and we have seen what are the basic formulas we use for differentiation.